or we had maybe been focusing on the theory of estimation, right? And in regards to that, we have seen what are the different properties of an what are the different properties of an estimator are. This next thing that we have checked is that what is what are the areas where estimation is ideally used. Also, we have tried understanding that what are the different kinds of estimation algorithms. So over there, what we get to see is the following: that a good estimator should have the so basically what we get to see is that a good estimator should have the following properties. One, unbiasedness; two, consistency; third is efficiency; and the fourth is sufficiency. So these are the four important things that estimator should good estimator should have. These are the four important properties, right? Now, after that, the next important thing that we get to see is we get to talk about the you know the different algorithms that are used for obtaining the best estimators. Now when I talk about the best estimator, what we are essentially referring to is an estimator which is unbiased, which is consistent, which is efficient, and which is sufficient. So one thing that we saw was that unbiasedness as a property of a good estimator is contingent on the sample size. Hence, to overcome the samples, hence to overcome the problems associated with a sample size of a with a given sample size or with sample biases. So one another property is the property of consistency, right? So over there, what we get to see is that as n tends to infinity, so as n becomes larger, therefore, when as n tends to infinity, what we get to see is that the elements are becoming, or the estimators are becoming more and more consistent in nature. And finally, what we saw was the element of sufficiency, where we get to see that an estimator is a sufficient estimator if it captures all information about the population parameter, right? So about the population parameter in the sense that it captures all the different characteristics that a population parameter has in terms of its mean and variance, right? So over here, so this is what we had kind of seen in the last class. And we had discussed about the different kinds of estimation algorithms like ordinary least square estimation, weight least square estimation, maximum likelihood estimation, method of moments. So all these are used to derive appropriate estimators for a given distribution, right? And we also discussed the areas where estimation is required in predictive modeling, in risk and predictive modeling. The question that comes out over here is why is it that we need these in risk, right? So what are we predicting in risk? So basically in predictive modeling, we are just trying to predict stuffs, right? Hence, what we are trying to do is we are trying to understand the difference of these uh, the different areas of these model development processes. Right? So, and over there, what we see is that the entire population is not always known to us. It's not is never known to us because we are predicting for a in predictive modeling. We are actually predicting for a period where we do not have any information on. We don't know what the future is going to be like. So if there is any disruptive behavior with the future, then the models might fail. So our objective over here is to develop the models or develop models based on the average behavior of the past, such that they give us proper predictions. Also, such that they help us predict the average in the future. So having said this, let us just have a quick look into this. Let us just have a very uh, quick understanding of the stuff that we are working with next. So next, our idea was to understand that. what exactly are the different sample estimators and their respective population parameters. And above all, one important thing that we wanted to understand in this session was the concept of significance. So basically, I say that the sample mean is not different from the population mean, but is not different from the population mean, or the sample mean approximates the population mean. So how is it that we can say that, right? So therefore, what we need to do is we need to find out the ways to test for significance, and that is where the concept of testing comes in, right? So before moving on to testing of hypothesis, there is just a few points that I would like to make, that I would like to discuss, right? So one very simple point is on the X bar, on sample mean and population mean, and on sample variance and population variance. So this is one big thing that I would like to make, and we would be connecting the concept of testing to this basic problem, right? So let us see how, and we always say that the sample mean is the best predictor for the population mean, and sample variance is the best predictor for the population variance. And from where this, and what we need to do from here is we need to understand that how is it that this development exercise, or how is it that this relationship holds for a given, between a given sample and a population, and to have this relationship, right, what are the necessary assumptions that we might have, what are the different assumptions that we might have. Now let us see. So let's just start the discussion right from the basics, right? So basically, you would see that whenever we are trying to represent a population, right, we always start on from the point of view that okay, let's look into the sample mean, and based on the sample mean we try to frame an idea about the population mean. So basically I'm looking into the sample behavior, right, into the sample portfolio, into the average receivables for a one given point of time, for a say for last 5 6 months, and I frame the conclusion, and the over the last year this is how the portfolio master behaves. So these have been the average behaviors. But so basically, when even if I'm using up the data that I have, right, so I'm always essentially working with a sample in a point of time. So why is it that we always use sample mean to study the population mean? And why is it we use sample variance to study population variance? And what are the respective formulae for these respective estimators and population parameters? Now, first of all, we would like to say that these, this X bar and S square that we call estimators, yes, they are estimators because they help us estimate the behavior of the population, right? But at the same time, also from being an estimator, they are also, you know, they are also a kind of something called a statistic, because they are an estimator with a distribution associated with it. And to describe an estimator and describe a statistic, we require two things. Again, we require a mean of that sampling distribution, and we require a variance of that sampling distribution. So today we'll start our discussion and try and explore the fact as to why sample mean is considered to be a good predictor of the population mean, right? So does sample mean satisfy all the properties that a population mean does? So this is what we need to understand in today's session. I know that these statistics sessions are going ahead for long, right? But having an in-depth understanding of these phenomena, of these factors, of these reasons is absolutely important for the next stages of development. Now, You might just do without these, because when you do it on a software, right, so these are something which is not required. But if you want to be a good, risk modeler, you need to understand that why is it that a particular stuff is happening, what is the statistical interpretation behind that. It is only then can you interpret each of the events, right, each of the occurrences. So all occurrences can be interpreted from a business side of things as well as from the statistical side of things, and at a point of time they go and they bridge together. So this is what we need to understand, right, as to how is it that, why is it that these things happen. If I am using sample mean, why am I using sample mean? Because if I know this and I know the assumptions or the reasons behind using this, so if I see that in a situation the one or two reasons are not getting satisfied, then I know that sample mean may not give me the good prediction, and then I know I need to move on to sample median or something. Otherwise, if I do it very in a very technical manner, or in a very told to learn manner, then what will happen is you would not be able to identify the reason. It's very important that you delve deeper into each of the causes that impact these statistical happenstances. And hence the logic that I am following in these sessions of going deep into these statistical portions, because the entire statistical framework which would be used now for credit risk modeling as well as for other versions of the model is based on certain pillars, or based on four very strong pillars of statistical modeling. And it is those pillars that we are exploring. We have done an overview of the two pillars, the descriptive measures and the theory of probability. Now we are into the statistical inference theory. After this comes the predictive modeling techniques, right? And within this statistical inference, there would be a lot of different kind of tests coming up, right? So we need to have a very good understanding of these statistical tests which are actually coming up, right? So therefore, from this part we need to, or this part needs to be absolutely clear in our minds, right? So in an interview, if you are ever asked that you are why is it that you use sample mean to predict population mean, why not sample median? Because median is a more robust estimator from the point of view that median is not affected by outliers. So if I am using sample median, I can avoid a lot of sample, a lot of outlier treatments, and can save out a lot of time, and then I go ahead and develop the model. Then why is it that I do so much of adjustments and keep back the mean as a method or as a model, right? So this is something that we are looking to explore. Okay, so starting about this discussion against this background, so let us start off with this particular discussion. So I have a population, right? Right, I have a population. So over here, I what I do is I take up multiple. I start collecting samples from here, and I create out samples. And I do this through repetitive random sampling, or whatever stratified random sampling is possible. But what I do is I create out multiple samples. So if this is the first sample, the sample mean over here is x bar of the first sample. Similarly, there is, say I collect another sample out of this. x bar 2, right? So these are some of these mean values that are there. Now what I do is I compute. So my objective is to frame an idea about the population mean based on the sample. And what I'm doing is I'm doing my simple random sampling. So let's for simplicity let us assume I'm doing it with replacement. Let's not complicate things further. Let's just try to understand the reasons. So let's say over here, this is the sample number that I have. So this is the sample mean that I have. So the sample mean distribution. And over here what I have is the frequency. So over here this is number one. Is x bar 1, right? So the first sample that I draw has a value x1 bar with a frequency f1. The second sample that I draw, there is x bar 2 and it has a frequency f2. So like this there are multiple stuffs and there is k. So what we have over here is f of 2. So over here what we have is the respective sample means and their respective frequency distributions, right? Now from here, okay, so before I move on, let me take the question that Piyush has. So what do we mean by frequency of samples? Shouldn't frequency be different for different events? Yes, Piyush, the frequency will be different for different outcomes. So basically what I'm saying is this is a value x1 bar which has come up, right, which has occurred some twice or thrice. Say for example, in this in sample 1, right? So suppose I have sample 1. In sample 1, there are three values: 10, 5, and 15. So the total is 30 divided by 3, which implies that the x1 bar or x bar value is 10, right? X bar 1 is 10. Now say that I'm collecting the nth sample. So over there what I have is 10, 0, and 20. X1 bar n of the nth sample is also 10, right? It means that this x1 bar value, right, has occurred two times. That is the f1, the number of frequency associated with the distinct value x1 bar is 2, or f1 is equal to, right? So this k number of samples that you are seeing is the k number of different sample mean values that have actually come up, right? So that is what I mean by the frequency. So it's not the frequency of the samples, but rather it's the frequency of the sample mean. So what is that value sample mean that has come up? Okay, so from here, so now what I want to know is that what exactly is the expectation, or what is the expected value of x bar. So what is the long run average of this x bar? So just let us, in case, let us remind ourselves that this is the mean of this population is. So over from here, what I can do is I can compute the expectation of x bar. Can any of you recollect as to what an expectation of x bar is? So what is an expectation, right? So what is an expectation? I believe we have discussed this concept, so I think we can actually try to answer this. What is this expectation x bar? No, I mean, yes, in a sense it's right, but what is expectation? I'm not talking only about sample mean, but I'm talking about expectation as a general concept. No, the expectation is nothing but the long run average of a random variable. Expectation shows, or expectation is nothing but it is the summation of I1 to n, or I1 to k over here, we are k samples. I want to k probability of x bar equal to x bar I into, right? So what is the probability of getting x bar I? X equal to x bar I, right? So probability x bar equal to x bar I into x bar I. So now over here, what we get to see is, so the question that comes out over here is what exactly is the probability of x bar equal to x bar? What is the probability of getting x bar equal to x bar? It is nothing but summation if I by n. Into. Now, for a sample mean, it is seen that I'm not going into population. I mean, I'm not going to mathematical derivations. So it is seen that this, for this case, in this case, it is expectation of x bar is equal to mu, right? So it is seen that the expectation of x bar is equal to mu. So the sample mean is an unbiased estimator for the population mean. And this is the first reason as to why a sample mean is always used to frame an idea about a population mean. But this relationship between the sample mean and the population mean would only hold if and only if this would hold if and only if the population from where the sample has been drawn, or and the sample itself is normally distributed with mean mu and various variance signals. So this is precisely the assumption behind which the entire population of the statistical inference theory stands. That this is one of the most important assumptions of the classical inference theory. This is the assumption, right? So over here, this is X which follows normal distribution, right? So the population from where the sample is being drawn, that sample has to be normally distributed. Now, having seen that next, right? What do we do over here? Uh, so over here, one thing that we can see is that this X bar itself has a mean. So if I'm computing the expectation of X bar, that is, if I'm computing the expectation for the distribution of X bar, then it means that expectation X bar has a definite value which is equal to the population mean. That is, therefore, this X bar has a mean. Now, the next part that we want to do is we want to derive. So now, if X has a mean, which is mu, X bar, I mean, if X bar has a mean mu, then X bar should also have a variance, right? So over here, what we do is we put in, we need to estimate the variance of this series, which is expectation of the variance of X bar, right? So there is a variance of X bar. So over here, what we have is we have expectation of X bar. So it means that this mean has, or this distribution has a mean. Also, the next thing that we can see from here is that this distribution should also have a variance. So what is the variance of this X bar? The variance of this X bar is expected value minus expectation of X bar. What we have is expectation of X bar minus the expectation of X bar minus X bar expectation X bar whole square. So what I'm trying to compute over here is try to compute the variation that X bar has from its mean. So over here X bar will be nothing but X bar minus mu whole square. So basically the X bar series, so all the X bars are not exactly equal to the, you know, not exactly equal to this okay. So what we are so all the X bar i's are not like related. I mean, they are not exactly equal to mu or the average value of a X bar of the X bar distribution. So there is always a variation. Now, this variance of X bar is also important that we need to know in order to understand this distribution. So, what is the variance of X bar? So, this variance is defined as sigma square by n, right? So, from these two, what we can clearly conclude is the following: that if there is this variable, if I have this X bar, this X bar series follows a normal distribution with a mean mu and the variance sigma square by n, right? So this is where it follows x bar, follows normal distribution with mean mu and variance is sigma square by n, right? So what I can now see is that this x bar is not just a value, right? So this x bar has been obtained from creating multiple samples and from there taking a distribution of x bars, and what I have is a resultant x bars. This x bar that I'm talking about over here is a statistic. So an estimator with a distribution attached to it is called a statistic, right? Now if it was not a statistic, if there was not a distribution, then I would not be able to compare whether it is statistically I mean statistically significantly different from mu or not. So for to expose anything to, you know, to the statistical testing, that variable or that x bar has to have a relation to, I mean that estimator must have a distribution associated with it. So this is what precisely the idea is. So what we get to see is that this x bar is a simple statistic, right? But observe one thing. So one thing is clearly observed from here, that since expectation of x bar is equal to mu, x bar is an unbiased estimator. Is unbiased. Is unbiased. Right? So X bar is an unbiased estimator of mu. Unbiased estimator for mu. Right? So X bar is an unbiased estimator for mu. Now, the next part that we have over there again is as follows. That since X bar represents all the characteristics of, you know, since it shows all the characteristics of represents all the characteristic of the population, right? So it reflects mu, it reflects sigma square, etc. Therefore x bar is also called a sufficient estimator for mu. So an estimator is said to be a sufficient estimator for a population parameter if it has the capacity to reflect the behavior of, I mean, reflect the different characteristics of the distribution of uh, a parameter estimate, right? So this is where this x bar is. So this is why x bar is considered to be a good estimator for mu. So x bar is considered is a sufficient as well as it is an unbiased estimator for the population mean mu. Now, similarly, given that it is unbiased, so we have seen that unbiasedness and sufficiency holds for this, right? Now, over here, one more thing is that is to be seen over here is that X bar is also a consistent estimator for you. How can you say that? So there is obviously a formal mathematical proof which goes beyond that. But over here, what we can also do is we can very easily try to understand, the kind of from this figure, right? So you can see that as n tends to infinity. So if n tends to infinity, sigma square n sigma square by n would tend to 0, right? So if n tends to infinity, then sigma square by n tends to 0, right? So if that happens, then what would happen? So if the variance starts falling, that means what? All these x bars would are come arbitrarily close to the population mean mu, right? So then there would be a case where x bar 1 would tend to x2 bar, x bar 2, that would tend to dot x bar k, which will finally tend to 0. So all these variables, all these sample mean will come arbitrarily close to mu. So from this discussion, we can also say that that x bar is consistent. X bar is consistent. So x bar is, so x bar is a consistent estimator for mu. So these are all the reasons you can clearly see from here that X bar is actually a very strong estimator, or we have very strong reasons to believe that X bar is a good estimator for me, right? Is this part clear? So one very common FAQ, one very so basically one very common FAQ in interviews, in analytics interviews or disk interviews, people when they quiz you on statistics, one very common question that they ask you is that what do you think is the difference between a statistic and an estimator, right? So basically a statistic is also an estimator, but it has a distribution associated with it, because so when we do testing exercises, right, when we do test, what we are trying to do is we are trying to ideally test. So we can only conduct testing exercises if and only if there is a, if there is a distribution to an estimator. It does not contain, I mean, so with just estimator with just one constant value, you cannot do a testing. For testing, you must have multiple samples created. And from their samples, you must have the distribution, and from those, you must have multiple values of the estimator, right? And from those estimator, from the distribution, you need to frame your understanding. So this is what the overall idea is, right? Now after this, the next question is, now the next question that we have over here is that the next question that we take up over here is that why then sample? So these are the reasons as to why we are saying that sample mean. is a good estimator, right? But then why not sample median, right? Why not sample median? Then why not construct the sample median as a measure of this, or as a, as an estimator for the population mean? So what is the problem that if sample median is taken? Now, ideally, sample median is a consistent estimator for mu. So basically, as n tends to infinity, the sample median would also tend to mu, because the reason is, as your n tends to infinity and your population asymmetries and your sample asymmetry start reducing, you start converging to a symmetric distribution, right? So when the distribution converges symmetricity, the mean will also tend to the population parameter, population mean mu, but also the median will tend to the mean, and hence the median will also tend to the population mean mu. Hence, both sample mean and sample median are considered to be consistent estimators for population mean mu. But the problem with median is that median is not a sufficient estimator for the population mean mu. Since median is just a positional value and it does not come with a distribution associated with it. But on the other hand, sample mean, apart from being a consistent and unbiased estimator, is also a kind of, so it is also a sufficient estimator for the population mean. So this is the reason why sample median is used. I mean, sample mean is chosen over sample median. Okay. So clear up to this. So are we clear on the reason as to why sample mean is chosen over sample median as an estimator for population? Are we clear on this one? Wonderful. Now let's just look into the next part. Now coming to the sample, the sample variance. So the population variance is sigma square, right? And we try to estimate the population variance using the sample variance. So ideally, the expectation of sample variance should be equal to sigma square, but it is not. So when we use this definition, a square is equal to 1 by n summation xi minus x bar. When we are talking about summation xi minus x bar, so this is a biased estimator. So this is a biased estimator. Right, so this is a biased estimator of sigma square. Right. So sigma square is not equals to the expectation value of S square. So therefore, what we generally use is an alternate measure is used, which we call say S dashed square is equal to 1 by n minus 1 summation xi minus x bar whole square. Right. So this is where we have expected value of s square, s dash square, so which is 1 by n minus 1 summation xi minus x bar whole square. Right. So this is how we have. So this is how this thing looks like. Right. So generally when we are talking about s dash square as an unbiased estimator or a square, so generally this is the one that we generally use. So this is unbiased estimator. So when we use Excel functions, right, so you'll see that there are two options for standard deviation. So one is the STTDV dot P. So that's the population standard deviation. So which stands for sigma, that is 1 by capital N summation xi minus x bar whole square, and the other is STDV dot S, which is the sample standard deviation. So that sample standard deviation is this particular version 1 by n minus 1 summation xi minus x bar whole square, because this version is an unbiased estimator for sigma square. Right. So this is what the overall behavior of the sample is. This is what the overall behavior is. Clear? Okay. So Anirudh, there's a question: why is this unbiased? So basically, if you use this formula, right, and you derive it, so if you compute the expectations of s dash square, right, square, so that is equal to sigma square. So this is as a result of a statistical proof. So I'm not going into the the intricacies of the statistical proof. I'm just highlighting the fact that to describe a distribution given a sample, we require the sample mean and the sample variance, right? So the sample mean that we use is the simple x bar equals to 1 by small n summation xi. On the other hand, when I talk about this expectation S bar is dashed whole square, so when I'm trying to find a an unbiased estimator for the population some variance of the population standard deviation, then S dash square equal to 1 by n minus 1 summation xi minus x bar whole square is an unbiased estimator, right? No, Anirudh, this is not a degree of freedom. So the degree of freedom will come when we are discussing the testing hypothesis, right? So this is just the formula. This is 1 by n minus 1 is the number of observations. Okay. So this is how. So this is what. So basically, so the sample that we have. So if there is a population X which follows normal distribution, mean mu and variance sigma square, then to frame an idea about, and this population is unknown, right? The population parameters mu sigma square are unknown. So from here, if we get to a sample, say which is small x, right? So the small x sample will follow a normal distribution with mean x bar and a variance s dashed square. Okay. So then what I'm saying is that this is the so if the population is this, then this sample will follow a mean with x bar and s dash square, and using these estimators or these statistics we can measure this population, or we can frame an idea about the population parameters, right? Now having said this, the next important question is, so the next question is that all these results that we are stating over here are theoretical results, right? However, what possibly can be, say, based on my historical experience, right? I know that the roughly the population mean that I'm trying to draw up is like 96. But when I compute the expected value of x square, what I get to see is it is 95.2. So will X bar be a biased or unbiased estimator? So X bar will be an unbiased estimator if and only if. So X bar is unbiased. So X bar is unbiased if and only if the difference between expected value of X bar and mu is significantly different. So if and only if the difference between expected value of x bar and mu is significantly different. Now the question that comes out is that how different is significantly different? How do I talk about a significant difference? So how do I quantify significant difference? Because what might be significant to me may not be significant to you, or what might be significant to you may not be significant to me. So how do I know what exactly is significant difference, right? So that is what we need to quantify. And to quantify this, and to quantify this difference, the concept of significant difference and all, what we have over here is the following. So over here, so that is where we bring in the concept of testing and hypothesis, or rather testing of statistical hypothesis. Yes. So, to your question, Anirudh. Anirudh has a question: then how will sample predict population if sample mean is significantly different from population mean? Yes, in that case, sample mean would not be able to do it. So, the sample mean can predict the population mean if you have currently observed, even only if the sample is normally distributed. So, if you have a normally distributed sample over here, only then can you see, then will you see that this difference is, or this is significantly, I mean, then we can see that expected value of x bar and mu, like x bar is a good predictor of population mean. But however, that does not necessarily mean that sample mean is always a good predictor of population mean. So if I just make that statement, then someone may come back and tell me that, man, why are you saying this? This is not always true. So how do I do that? How do I, you know kind of, how is it that I would get along with that? So this is the part where we need to talk about this part of testing and hypothesis. So this is where we need to assess whether expected value of x bar and mu is significantly different or not. In other words, very generally speaking, we need to assess whether a estimator and a population parameter are significantly different or not. Rather, more precisely, whether a statistic and a population are significantly different or not. So this is what we need to know. Right. So, given that a population is normally distributed, it has been tested that the expected value of x bar tends comes very close to mu, right? But however, again, if we are empirically trying to establish that, then empirically, expected value of x bar may not be exactly equal to mu. There might be some differences, right? So, how do we know that there are these differences, right? So this is where, this is how this entire part is. So this is where the role of testing actually comes in. So we need to test. So whenever, say, I have obtained a beta hat, or say I have obtained any estimated value, I need to test whether this value is significantly different from a population value or not, or the predefined population value or not, or whether this value is not significantly different. So how does it work? So this is what we need to assess, right? So over here, what we have is we have this testing of. So over here, what we have is this expected value of x bar and mu, and there is this difference and so on. Now, when I talk about testing of a hypothesis, right? So you can understand that this hypothesis that I am talking about is to test whether a difference is significant or not, whether it is significantly different or not, or to try and is try and test a significant difference. Now, in statistics, any quantity or any difference is not a difference until and unless it is statistically significant. Generally, what we get to see is the following: that in statistics there are two kind of differences. One is an observed difference, and the other is a significant difference. Right? So there are these two differences. Now the question that comes out over here is that how is it that I would identify whether a difference is a significant difference or whether a difference is a observed difference. So if it's just an observed difference, I do not really bother about it. I say that okay, this is just because of sample variations, this difference is occurring, but there is nothing really substantial about it. On the other hand, if a difference is statistically significant, only then I will be bothered about that difference. I'll say that okay, this difference is a statistically significant difference, so I am bothered about it. So now the question that comes out is that why is, so two questions. Number one, why is significant difference something so stressed upon? That's one. The second is, why is it that, or how is it that we distinguish between the concept of an observed difference and a significant difference, right? Now suppose, so let's take an example. Okay, let's continue with yesterday's example. So in yesterday's example we saw that, so there was a loss rate variable. So we said that okay, there is a loss rate, the loss rate, and if no recovery is actually initiated, the loss rate is 0.05, and for every unit of recovery the loss rates falls down by 0.0002 units into recovery. So basically what it says is that every time, so what I'm trying to assess is a causal relationship between recovery and loss rates, right? So there must be a causal relationship between the two, right? Now, what ensures that there is the causal relation? It is this value. It is this value which ensures that there is a causal relation. So what I'm saying is that, man, I can see that there is a difference. Right? Now, is this so? Every time the recovery is increasing, right, the loss rates are going down by some proportion. So the question that comes out over here is that is these are very significant proportion by which the loss rates are going down, or is it as good as not going down? So basically over here, if this 0.0002 is a number which is not significantly different from 0, then I'll know that then I can say that this recovery process is not, or the recovery amount is not significantly impacting the loss rate. So the causality that you are seeing over here is just because of sampling fluctuations. This is just an observed causality. There is nothing significant about it. It is not having a significant impact on my loss rates. So that is where I need to assess, I need to distinguish between a significant difference and an observed difference. So what I'm always trying to assess over here is that should I be, so if this recovery was to increase, right? So if this recovery increased by say 5%, so what will be the impact on the loss rates? So how much does the loss rates go down? So is that impact a significant impact, or is it as good as not having an impact? So what I want to understand over here is that, say if I call this is the beta hat, right? So I'll say that this beta hat is equal to 0 versus beta hat not equal to 0. Clear? Okay. So over here, what I always want to understand is that, does this impact the loss rates significantly? So what I need to understand over here is two things. So how do I test for a significance? So how do I distinguish between an observable and a significant difference? And the second question has been answered over here, that why is it important to have a significant difference? So if this value is not significantly different from 0, it means that the recovery would not have any impact with the loss rates, on the loss rates. So there is this significant. So this is the reason why we need to understand whether there impacts a significant difference. Now, if there is no significant impact of recoveries on the loss rates, then it is as good as not using this model, because I'll use this model, I'll implement it in my systems, I'll bear a cost for it, and then not get any significant reduction in loss rates, then that is not worth it. So from the business perspective, like putting in statistically insignificant variable would not be much of a help. Hence, it is important to test for all these variables, right? So this is where this is loss rate is 0 point. So basically, what we need to assess over here is that whether a difference is significant or observed. Right? Is this idea clear up to this point? Are you guys clear with what I'm trying to say? Any questions, any queries? Take 2 minutes, think about it, and ask me if required. Because trust me, this part is actually very, very, very critical. Great. So now, after hearing to all this, what do you think is a difference between a significant change, a significant increase or decrease, and an observed increase or decrease? What do you think is the basic difference between these two. After listening to all these discussions that we have had till now. Yes. Then what do you think is the difference between an observed yeah, the difference between observed difference and a significant difference? After listening to the discussions that we have had today. Yes, please tell me. Don't be apprehensive of getting it right or wrong. Just tell. Okay. So the question is, what do you think after listening to the discussion that we have had till now? Right. Consider this example as well. This particular example. And tell me, what do you think is the difference between observed difference, right, and a significant difference? Okay. Compared to the population mean. Okay. No, basically what we need to test whether that difference is an observed difference or a significant difference, right? Uh, no, Preeti, not quite that. Okay, I'll tell you. See, an observed difference is just a difference, right? It will not have any real impact on the results. So, for example, say if this value 0.0002 is an observed value, so it's a value which has just an observed difference from zero. So, all I can see is that okay, this is 0.00002. So it means that okay, this is just a number greater than 0, but it is as good as being equal to 0. So it means that if recovery increases, the impact that I have on the loss rates is not worth it. So it is not, it is as good as not having that impact, right? So that's what is observed difference. From the next part, if you have a look into this, you have the significant difference. So if a difference is actually significantly different from 0, it means that it is a number which has a significant, that difference is significant in the sense that that difference will have an impact on the dependent variable. So, so every unit increase in recovery will cause the loss rates to go down by 0.0002, and that is actually a significant amount. So that impact is actually very significant on the dependent variable. So basically what we can clearly, in the very simple words, what we can say is that an observed difference is a difference which makes a real impact, it affects the outcome, it changes the outcome. Whereas a observed difference is a difference which does not change the outcome as such. Let's take a simple example. Say, for example, you have given a mathematics exam, right? You gave a mathematics test, and your pass mark was 40, right? So this is where you had this is where you had given a maths test, and there were two candidates who had given this test. One candidate got 35, another candidate got 38. Okay, so over here there are these two people, one got 35 and one got 38. So both of them saw that a marks of question of 3 marks has not been correct. So what they did was both of them went to the teacher, and the teacher, checking their results, I mean checking their answer scripts, increased the marks of both the students. So after getting plus 3, this guy moved from 35 to 38, and this guy moved from 38 to 41, right? So one guy moved from 35 to 38, and the other moved from 38 to 41. Now observe that for this first guy, the result did not change. So he was at 35, he moved on to 38. At 35, he was failing. At 38, he is also failing. So his outcome does not change. Therefore, this difference that we have is called a observed difference. So this increase that happened over here, this increase is a observed increase. And this increase is a significant increase. Why? Because this has impacted the outcome. This is a significant increase. So this has impacted the outcome. So therefore, both these cases you see the increase is by 3, right? So it is not that all nominal amount by which the increase is happening, but rather what is more important is that uh, you know the amount by which the impact that this increase has on the value. So therefore, over here, what we get to see is that there is observed increase plus. So the first case, the plus 3 increase is that of an observed increase. The second case, what you get to see is that's a significant increase because the second increase is actually impacting the marks. So the significant or the observed, right? How is it defined? It is defined in terms of two values. One is a critical or a benchmark value. Critical or a benchmark value. And another is an actual value. So using the benchmark or a critical value, and the second is using an actual value. Now, by comparing the critical and the actual, what we do is we decide whether an increase or a difference is significant, an increase, decrease, or a change is or a difference is significant or it is just an observed difference. So that is how we decide on that. Clear? So this is what a significant and an observed difference is. Just check this concept. Have you understood this concept? So this concept is important. Now, so basically, when we conduct the concept of statistical testing, right? So keep this example handy because I would be referring to and fro, back and forth to this example. Now, when we talk about statistical hypothesis or testing a statistical hypothesis, so in that respect, we will bring in some very specific concepts. The first concept is null hypothesis, or even before that, let's start off with the concept of hypothesis. What do you think is hypothesis? What is a hypothesis? One word. What is a hypothesis? Any assumption, okay? uh, Not an assumption really. Hypothesis is a conjecture. So hypothesis is generally a conjecture. So hypothesis is essentially a conjecture which I generally have in mind and I want to validate. So basis a set of results that I have obtained, basis a set of numbers, I have framed a conjecture. However, a conjecture necessarily need not be an assumption. So an assumption is generally a set of necessary conditions which we require for performing any exercises. Right? So for example, for doing a testing, I need a population to be normally distributed. So If I have not tested for that, and while I'm theorizing it, if I'm talking about theoretical framework, it is there that you know we'll talk about. So then it is an assumption. But generally, what happens is, say for example, the difference between sample mean and the population mean. So what we have done is we have actual calculation and we see that we have obtained two values. So now what I'm trying to do is I'm trying to develop a conjecture. I'm trying to conjecture whether this difference is significantly different or not. So I have a calculation done basis which I'm creating a conjecture. I'm trying to create a conclusion. Now when I prove this conclusion, this is a thesis. When I cannot exactly prove the conclusion, it's a hypothesis. So over here what we are trying to do is we are trying to assess that, so basically, I'm trying to understand whether a difference is significant or not. So I'm in a two state of mind. So what I do is I try to build in this. So what I'll tell is that okay, there is a difference. So I'll say that the first conjecture that I have is a null conjecture. The first conjecture that I have is a null conjecture or a null hypothesis. The null hypothesis, as it suggests, it is always the no significant difference hypothesis. So over here, if I'm talking about in respect of the, this expected value of x bar and mu, my null hypothesis will be expected value of x bar is equal to mu versus the alternate hypothesis value of x bar is not equal to mu, right? So the first difference tells me that, or the first hypothesis that I have over here is a null hypothesis. So it tells me that there is no significant difference between expected value of x bar and mu. Whatever differences we have, this is just an observed difference. Just observed differences. Right? And over here what we have is this says that no, this is a significant difference. So what we try to say over here is that whatever the difference that we have over here is a significant difference. So this difference, whatever we have over here, is a significant statistical difference. Right. So over here, what we are trying to do is we have this alternate hypothesis, right? So expected value of x bar is not equal to mu, and over here it is expected value of x bar is equal to mu. So we just have this observed and the significant difference over here, right? So these are the two hypotheses. So the first hypothesis is a null hypothesis, and the second hypothesis that I have is the alternate hypothesis. Right, so these are the two basic hypotheses that we have over here. Clear? So now the next question that comes out is that how do we or how would we test for this difference? So we need some benchmarks to test, right? So over here, when we are trying to test, there is a decision rule that needs to be done. And first of all, I need a test rule or some. So I need to first of all generate this actual value. So for doing this, what I would have over here is the test statistic. So the first and the most important, the ingredient for conducting a statistical test will be a test statistic. Now, once we look into this test statistic, so once we look into this test statistic, right? So this test statistic will divide the entire region, the entire testing into two regions: acceptance and rejection. Acceptance and the rejection. So over here, this marks that I obtained over here is the actual, the test statistic, and it is this critical value which is helping the test statistic to divide, which is enabling the test statistic to divide the region between two parts into an acceptance and into a rejection value, right? So it is this way that the entire thing happens. So over here, the acceptance and the acceptance and the rejection is done in terms of two values, right? So acceptance and rejection is done in terms of a critical value. In terms of a critical, right? So this critical value is a test statistic value. Now another rule that we use to assess the this kind of behavior, this assess to assess the acceptance and rejection, is also the concept of an error error or the error commission chances. So given the error commission chances, we do have a way of accepting this, doing this acceptance rejection tests. So the acceptance and the rejection is done in terms of the error. So this acceptance and rejection. So the chances of committing the errors also help us to go into this, or also help us, to derive this error commission chances. So it is this part where this acceptance and the rejection needs to be looked into, and the two error concepts that we need to look into are: number one, the alpha values, or I mean the level of significance, and the p-value. So people who are into analytics and who are working into analytics, you'll hear a lot of them talk about this concept of level of significance, and they talk about p-value. And the second concept that we will talk about is right. So let's take a pause over here for the day, right? I am sending over these updated whiteboards, right? So what you can do is you can start going through these concepts. Next class we finish off testing, and we start off with the scorecards and the risk management, the credit risk proper portions, right? Thank you guys. So I'm done from my end, and please reach out to me in case of any queries or anything that you might have, and we can take it up from there. Yes, I have learning materials. I will share it over by not today, by tomorrow or Tuesday, because I have to send it out to a couple of batches as well. So I send it out through to the batches directly. Right. So it's a Word document. It's completely typed notes on central tendency, dispersion, probability theory, and so on. So you have this entire paths through which you can actually go through. So it's a lot of learning materials. There are a lot of mathematical derivations as well. So if you want, you may skip the mathematical derivations. If you are interested, you can go through them. So it's an entire strict documentation, right? So this material has been developed. So I developed this material along with one of my colleagues, Akash. So he works with me from Calcutta. So you can directly reach out. So in case of any queries, you can reach out to me or to Akash for clarifications, right? So just mail it to me. In case I am unable to reply, Akash will get back to you. So that's okay. That's not a problem. I'll share over the learning materials, right? Thank you guys. Bye bye. So next week we finish this testing portion and we start off with scorecard development. I mean, we talk about we start off with scorecard, risk management using scorecards, regulatory modeling, etc. Okay. Bye bye. Thank you guys. Have a great week ahead. Thank you, Srinivas.